Hello. Okay, so I hope both of you understand me. You can hear me and you can see the screen. In previous class, we completed two techniques of medical imaging. First one we discussed was X-ray, then we discussed CT scan, and then we solved two or three questions related to CT scan. But we have solved just one question for X-ray, so we will try to solve at least two more questions for X-ray. If we get time, we will be discussing ultrasound in today's lecture. So both of you are trying to solve this question. This is question number 3, page, I can tell you in the booklet, it should be page 175. Question 3, page 175. Try to solve this question. Once you are done solving it, let me know. We will discuss the answers.
Sir, may I know what topic is this?
This is X-rays. Now we started medical imaging. And in medical imaging, there are 4 techniques. So first was X-ray. Second is CT scan. So CT scan question we solved in previous class, but for X-ray we solved just one question. So I will surely try to upload the lecture so that I can share with you because you missed both the sessions. So topic is basically X-ray.
Okay, sir. Sir, I'm not gonna be able to solve, but I'm gonna be listening to your explanation. Is this fine?
Yeah, sure. Okay, so I think only Anas was supposed to solve this question. He is done, so let's discuss the answer. An aluminum block is placed near to a small source of X-ray radiation as shown in figure 10.1. We have an X-ray source, we have an aluminum block, and there are 2 points marked A and B. X-rays from the source are detected at point A and at point B. State two reasons why the intensity of X-ray beam at point B is not as great as the intensity at point A. Now see, there are a number of reasons for this. One of the easiest point that should come to your mind is basically the absorption. Because X-rays will surely get absorbed in the aluminum block, quite possible because Anas attended the session, so quite possible to remember. He remembered that X-rays are of two types, soft X-rays and hard X-rays. And we want to separate soft from hard. So what we used to do, we used to put aluminum plates in front of the window from where X-rays are emitting so that we can absorb the soft X-ray radiations. So aluminum block has tendency to absorb radiation. So one is absorption in the block, because of which intensity at A is more and intensity at B is less. One is absorption. Now, second thing, remember one thing, when a wave is traveling and it strikes a surface, both things can happen, reflection and refraction. For example, if I say this is a piece of glass and a ray of light is traveling like this, I hope you can see at the top right of the screen, I just draw a ray of light or ray of wave or wave in pink color. What will happen? Some will reflect and some will refract. So this is characteristic of all the energies. No matter it is sound, it is light, it is wave or thermal wave, anything that is traveling in the form of wave, when it strikes the boundary of a medium, some part of it will be reflected and some part of it will be refracted. Now, what amount is reflected, what amount is refracted is actually depend upon the nature of surfaces. Quite possible when we will be discussing ultrasound today, I will explain this point again. Okay, let me do one thing. Reflection and refraction, most of the time when I use the term, students usually find it hard to distinguish them. So let's do one thing. Reflection is reflection, and instead of refraction, I can use the term transmitted, because transmitted means it is entering the other medium. So what will happen when X-rays will strike the aluminum block? Some part of the X-ray might be reflected from the aluminum block. So when it is reflected, so the intensity reaching B is less. So what we can say, the next point could be reflection at boundary, air and aluminum boundary, I mean. These are 2 points. There could be many. When X-rays are traveling, I hope you people remember, we always prefer a smaller source to generate a sharp image or sharp X-ray image. If source is big, rays will be diverging actually. So if beam of X-ray is diverging, so naturally the intensity reaching B will be less. Just assume X-rays are traveling like this. So when they pass point A, they were relatively close. When they reach B, they are relatively far. So intensity will decrease. So you could have mentioned the idea of divergence or diversion. Next, scattering. I'm mentioning all four possible reasons. You were supposed to mention any two. Yes, and as which two you mentioned actually?
Sir, the first one and diverging rays.
And divergent. But are you getting the remaining two?
Yes, sir.
Okay, Miram, were you able to understand? these points?
Yes, sir.
Okay, now next. A cross-section through a model is a finger is shown in figure 10.2. Now just try to visualize. If you point your finger, index finger towards you. So when you point index finger towards you and you look at the cross-section. So this is the soft tissue part. And this is the bone inside your finger. So this is actually cross-section of a finger. The thickness of the model is 2.4 centimeter. And that of bone in the model is 1.1 centimeter. Parallel beam of X-rays are incident on the model in the directions AB and CD as shown in figure 10.2. Data for the linear attenuation absorption. I hope we remember this equation. I, intensity of transmitted X-ray is actually intensity of incident X-ray divided into e raised to minus mu times x, where mu was the absorption coefficient and x was the thickness. And ma'am, just to remind you, remember when we were discussing radioactivity, we discussed this kind of formula over there,
Yes, sir.
exponential. So this is prototype. Whenever something is decaying exponentially, something is suffering attenuation. Attenuation means decrease in intensity. We use this formula. Intensity of X-ray beam incident on the model, that is I, and intensity of X-ray beam emergent from the model, that is, in fact, incident is I naught, and intensity of X-ray beam emergent from the model. So can I say we need to calculate I naught over I? I need to calculate I naught over I because I need incident over emergent. So it will become 1 over e raised to minus mu x, which will become e raised to mu x. I naught over I. Now, first we need it for AB. Now, beam AB is passing through soft skin all the time. So what distance it has traveled? 2.4 centimeter. And absorption coefficient for soft tissue is 0.27. Take care of the unit. The given value is in centimeter inverse. So it means that I don't need to change the thickness into meter. I will directly use 0.27. So I will calculate it like this. I naught over I is equal to e raised to mu. Mu is 0.27 into x, which is 2.4. So if I simplify this thing, yes, Anas, did we use the same formula?
Yes, sir.
So what are we getting?
1.91.
1.91, and it won't be having any unit, right? So we can say, by the way, they have given you two values and both are in two significant figures. So I think it's better to write just 1.9. Mira, were you able to understand this working?
Yes, sir.
So we got for AB. Now CD is interesting. Why? If you look at CD, it is passing through soft tissue. It is passing through bone. So it will suffer attenuation twice. One for the soft tissue and one for the bone. So if I want to write formula, I naught over I, there must be twice two factors involving mu x. If you understand this equation directly, it's fine. Otherwise, what you can do? Form an equation like this. What is here and what is here? Just combine them. You will eventually be able to get the same equation because X-ray beam will suffer attenuation twice. Once in soft tissue, which is e power mu x, once in bone, which is e power mu x. So let me do one thing. This is for soft tissue. This is for bone. Now, if I put the value for soft tissue, coefficient is 0.27. Now, what is the thickness for soft tissue now? Only the yellow highlighted portion. Can I say it is 1.3 centimeter? Because the width of soft tissue is 2.4, but 1.1 is actually the bone. So in this region, thickness of soft tissue should be 1.3. Now, for bone, mu is 3 and width is 1.1. Yes, sir. Did we use the same equation?
No, sir.
What did you do?
Sir, I left it blank.
Okay, but are you getting it now?
Yes, sir.
Okay, so just calculate and tell me what are we getting. Mira, were you able to understand this working?
Yes, sir.
Okay, so just calculate it and tell me what are we getting as the answer.
38.5.
38.5. Okay, use your answers in B to suggest why this model and X-ray image with good contrast may be obtained. Now remember how to increase the contrast. Contrast is good when one is absorbing X-rays a lot and the nearby region is not able to absorb the X-ray. Anas, remember this point.
Yes, sir.
So contrast means how easily you can distinguish bone from tissue. Now, if you look at the absorption capabilities of soft tissue and bone is 3 per centimeter and soft tissue is 0.27. So it means that there is much greater absorption in bone than soft tissue. So this will help us in obtaining higher contrast ratio. If mu was almost the same for bone and soft tissue, then image won't be very having higher contrast. So you won't be able to differentiate the gray area and the white area. So it means that you can say higher absorption in bone. Higher absorption in bone. It is just 1 mark question, so a single line will work. Now, if we were able to solve this question, question number 4 we actually solved in previous class. Okay, this is question number 6, page 179. Okay, so let's discuss the answer for this. Distinguish between an X-ray image of a body structure and a CT scan. So when we talk about X-ray image, so X-rays image are 2D images. And when you say 2D images, you need to mention one thing very important. No information of depth. I hope, Anas, you remember, I gave example of 3D movies and I said when we obtain 2D images, we just get height and width. We don't get any information about the depth. So when I say 2D image, it means that you won't be having any depth information. This is something we need to mention by. Let's say this is the organ, this is the scar. Now, X-ray can read this thing, this height and this width. This is 2D. But X-ray cannot read this thing. This is height and this is the width or depth. X-ray images can never produce depth information. They are always superficial. They always give you information about the surface. So regarding X-ray, what we can say, 2D images with no information of the depth. If we talk about CT scan, so CT scan are built from by X-ray images taken from different angles. So you can mention multiple 2D images from different angles, process to produce 3D image, and this 3D image actually give us depth information as well. Yes, Anas and Miram, are you able to understand this answer?
Yes, sir.
Yes, sir.
Okay, data for the linear absorption or attenuation coefficient mu of X-ray radiation of energy 80 kilo electron volt are given in figure 11.1. For aluminium, it is 0.46 per millimeter. And for copper, it is 0.69. Now, always note this unit. It is in millimeter. A parallel X-ray beam is incident on a copper filter as shown in figure 11.2. Calculate the thickness of copper required to reduce the intensity of the emergent beam. Now we need the thickness since mu is in per millimeter. So final answer is in millimeter. So always take care of this unit. If this is centimeter, your answer will be in millimeter, but you need to convert it into centimeter. Now, how will you do it? You will say I is equal to I naught e raised to minus mu x. Now, this I is actually 0.25 I naught because question says calculate the thickness of copper required to reduce intensity of emergent beam to 0.25. E raised to minus mu. For copper, the value of mu is given and which is 0.69. X, I naught will get cancelled. So we can solve this equation. So if we have solved it, may I know what are we getting as X?
2.01.
2.01. So X is 2.01 millimeter. Miram, were you able to solve this part?
No, sir, but I understand it now.
Okay. An aluminum filter of thickness 2.4 millimeter is now placed in the X-ray beam together with the copper filter in one. Calculate the fraction of the incident intensity that emerges after passing through the two filter. So let's talk about the impact of aluminum. You will say I equal I naught e raised to minus mu x. I naught, if I'm calculating I over I naught, what fraction aluminum will absorb? So it will become e raised to minus mu. For aluminum, the value of mu is 0.46. Into x, and x is 2.4 here. So if I simplify this thing, what I will be getting? Anas, did you calculate this value?
Yes, sir, but you're missing one part of it.
Which one?
Sir, the copper filter is also placed with the aluminum.
No, actually, I'm first calculating for aluminum, then I will talk about that.
I calculated it directly.
Okay, you calculated directly. What are you getting?
0.08.
0.08. Okay, if you are using the idea that I explained here, you use similar equation, right? This one.
Yes, sir.
Okay, so let me explain both the method. So you will be having multiple ways to solve it. If I add e raised to minus mu x, this one is for aluminum and this one is for copper. So you can say minus mu for copper was 0.69 and x we have calculated to 0.01. If I solve this value, we will be getting 0.083. This answer is correct, 0.083. Now, why I didn't put this value? See, this is something we already know that this value is 0.25. That this value is 0.25. So if I just calculate this factor and then multiply it by 0.25, I strongly believe we will be getting same answer. You can verify. Let's just calculate this value and tell what are we getting.
0.33.
And if I multiply 0.33 with 0.25,
Yes, sir, we're getting the same answer.
so we will getting the same answer because this is actually an overhead. The yellow highlighted portion is the one using which you calculate 2 millimeters. So if I put 2 over here, so I will be getting 0.25. Are you getting it?
Yes, sir.
Yes, sir.
Okay, so you could have solved question two different ways. By the way, the last part, express your answer into as a gain in decibel. Now, this is something you cannot answer now because for that we have to discuss communication first because decibel we will be studying over there. But just for the sake of understanding, once you got this value I over I naught, just take log of it. You will get answer in bell and multiplied by 10 will make it decibel. I hope you are unable to understand anything. So last part is not related to X-ray. It is actually related to how to calculate gains and all. Okay, let me complete the working. If you need gain in bell, bell is actually the unit of gain. It is log of I over I naught. If you need gain in decibel, it is 10 times log of I over I naught. So I over I naught we already know 0.083. Take log of it multiplied by 10. By the way, Anas, did you complete this question?
No, sir.
Okay, but formula is straightforward. I hope you will remember it forever. But when we will be discussing communication, there we will be using this formula at number of places. So since in exam they assume that the student has actually studied everything, so they mix this part. I think we should solve one or two more questions related to X-ray. So let's see in any recent paper. Because in the booklet, we have only these three questions. One we solved in last class, two questions we solved today. So if we see, May, June 16. It's a good question, actually. It's a good question because it's a 8 mark question, and there is not a single calculation. It's a complete descriptive or theoretical question on X-ray. Okay, after discussing this answer, just remind me, I need to explain one more point related to X-ray. So after explaining this, we will okay. Yes, Anas and Miram. I hope both of you can hear me and you can see the screen as well. So, question is actually in front of you. Try to answer this question. Okay, so let's quickly discuss the answer for this part. High energy electrons collide with a metal target producing X-ray photons. The variation with wavelength of the intensity of the X-ray beam is illustrated figure 12.1. I hope we remember that this is known as continuous spectrum. And I explained your term Bremsstrahlung, German word which means breaking radiation. These radiations are produced when electron is decelerating in the anode, right? And these peak represent characteristic spectrum, which means when electron make transition from any outer orbit to fill the inner cavity, right? So explain why there is a continuous distribution of wavelength. So why there is a continuous distribution of wavelength when electrons are entering or hitting the metal target, they keep on decelerating. When they keep on decelerating, they emit photon of different wavelength because they will be decelerating with different accelerations or decelerations, right? So what you will say, a continuous distribution of wavelength, it's a 3-mark question. So you need to mention 3 points. Number one, why do we have continuous spectrum? Because of deceleration of electron in the metal target, number one. Number two, electron will be decelerating with different amount because we have millions of electrons. All electrons are decelerating at different rates. So when they are decelerating at different rates, so they are emitting photon of different wavelengths. So these 3 points we were supposed to mention. Yes, Anas and Mira, are you able to understand this thing?
Yes, sir.
A sharp cutoff at short wavelength. Now, when they are talking about sharp cutoff at shorter wavelength, now what was the cutoff? This is the point where electron will give its energy. Electron will give all of its energy, or electron will stop in a single collision. Because if you see this point, this is cutoff actually. It means that this represents the electron which will stop instantaneously, but they are very less in number. But these electrons are very less in numbers. So in this question, what you are supposed to say, electron will give all of its energy in one interaction, or electron will stop all of sudden or instantaneously. A series of peaks superimposed on the continuous distribution of wavelength. So what is represent? It represent jump of electron from outermost orbit to innermost orbit. The jump of electron from outermost orbit to innermost orbit, or instead of jump of electron, you can use the term like de-excitation of electron. That makes sense. De-excitation means jumping from outer orbit to inner orbit. In the X-ray imaging of body structures, longer wavelength photons are frequently filtered out of the X-ray beam. Instead, how this filtering is achieved, I did put this thing a couple of times in today's class as well. Aluminum sheet. We will make use of aluminum sheet to absorb soft X-rays. Longer wavelength means soft X-rays. Last part is suggest the reason for this filtering. Because long wavelength cannot pass through the body, so they will get absorbed. So we need to get rid of them. Anas, getting it? Did you mention similar thing?
Yes, sir.
Okay, this will be last question for X-ray. By the way, the one thing I was saying, I didn't code while teaching XA was the use of intensifiers. If you want a sharp image, you need to expose patient body to X-rays for a longer duration. So what we usually do, we use intensifiers in X-ray film. It means that they will intensify the impact of X-rays hitting the photographic plate. Anas, this statement makes sense.
Yes, sir.
So that short exposure will give you sharp images. Okay, so solve this question once you are done with first page. Let me know. I will scroll down so that you can solve the remaining part. By the way, is this question readable now?
Yes, sir.
Yes.
Okay, then solve it. Once you are done solving it, let me know. We will discuss the answers.
Sir?
Yes, Vinam.
Sir, I need to leave right now because I need to go do the PCR.
You're sure?
Thank you, sir. Sir, when will you send me the recordings?
Inshallah, by tonight or tomorrow morning. I will surely upload both the lectures.
Okay, sir. Could you just send it to me before Tuesday so that I can catch up?
Okay.
Thank you so much, sir. Sir, do you mind if you send me this recording too?
Okay, I will share all three recordings then.
Thank you so much, sir. Thank you. Bye, sir.
Anas, done solving the entire question?
Yes, sir.
आजकल जो है ना थोड़ी एहतियात करो, केसेस बहुत बढ़ रहे हैं.
सर मैं तो निकलता ही नहीं हूँ घर से बाहर.
जिम भी नहीं जा रहे हैं.
बस वही 1 घंटा जाता हूँ फिर आ जाता हूँ.
तो जिम में तो तुम्हें पता है तरह तरह के लोग आते हैं, वहीं तो एहतियात करनी है.
जी सर.
अच्छा, okay. So explain what is mean by sharpness and by the contrast on an X-ray image. So sharpness mean how easily you can detect the edges of the image, right? And contrast means difference in the difference in the degree of blackening of the X-ray, right?
Yes, sir.
Okay. A parallel X-ray beam of intensity I is incident on a medium of thickness X as illustrated in figure 10.1. The transmitted intensity is IT. Data for the linear absorb. Okay. Instead, with reference to the production of X-ray, what is mean by 80 kilo electron volt X-ray? So, what is mean by this? The
Sir,
electrons have been X-rayed through this potential difference. So,
Yes, sir.
the maximum kinetic energy electron will be having will be equal to 80 kilo electron volt, right?
Yes, sir.
Okay. Calculate the ratio IT over I for 80 kilo electron volt X-ray passing through thickness of 1.4 centimeter of bone. Is it 0.015?
Yes, sir.
Okay. An X-ray image of the upper leg of a strand is produced. Part of the X-ray beam passes through a comparatively large thickness of muscle and part pass through some muscle and the leg bone. Use data from figure 10.1 to suggest whether the image has good contrast. Yes, what do you think?
Sir, it will have good contrast.
Because the coefficient of linear absorption for bone is much more than that for the muscle. I guess this is the same value as we use for the finger thing, right?
Yes, sir.
3 and 0.27. So it's a good contrast. Okay. So now we have 19 minutes. We can discuss few things related to ultrasound. Okay, when we talk about X-rays, there are some medical hazards associated to X-rays because when these are radiation, they can cause ionization as well. And we know that human body contains bones and they are composed of calcium compound, right? So many people say that these radiation can cause ionization. So the safer approach to study internal organ or internal structure is basically ultrasound. And what are ultrasound? When we discuss sound waves at IGCSE level, we usually discuss there's a range which is known as audible range, which is from 20 hertz to 20,000 hertz. Any frequency above 20,000 hertz is known as ultrasonic, and the sound is known as ultrasound. So what is ultrasound? Ultrasound is a medical imaging technique in which we make use of ultrasonic sound waves. Now, how we can generate these ultrasonic sound waves? Remember, sound is generated by vibrating body. For example, if frequency of my sound is, let's say, 1000 hertz, what does it mean? My vocal cords are vibrating at 1000 hertz. If frequency of a guitar string is, let's say, 300 hertz, what does it mean? The guitar string is vibrating with a frequency of 300 hertz. So frequency of sound is same as the frequency of vibration of the source. So if we need an ultrasonic sound wave, we will be needing a source that can vibrate more than 20,000 times in a second. I was getting it.
Yes, sir.
For that purpose, we use quartz crystal. Quartz is basically silicon dioxide, SiO2. These are silicon dioxide or quartz crystal, and there is a specific type of arrangement which is known as piezoelectric material. When we will be discussing direct sensing, I will surely make reference to this thing. See, what is a piezoelectric transducer? Transducer is any device that can convert sound into electrical pulse or electrical pulse into sound. For example, mic is a transducer because when you speak, mic converts your sound into electrical pulse. Speaker is transducer because speaker takes the electrical pulse and transform into sound. Getting it? So transducer is any device that can convert electrical signal into sound or sound into electrical signal. What is piezoelectric material? Piezoelectric materials are the material when we exert pressure on them, electricity is generated in them. When pressure is exerted on them, electricity is produced, and vice versa is also true. When electricity is allowed to pass through piezoelectric material, they deform, they change their shape. For example, let's say okay, this is just a rough sketch. Let's say we have quartz crystal, that is silicon dioxide. It is something like this. It's a piezoelectric material. Why? If I connect a plate here, it could be of silver or any metal, one plate here. If you exert pressure here and if you exert pressure here, you are trying to compress it. Electricity is generated in it. If you try to pull the plates apart, once again, electricity is generated. So we can say when you compress or when you stretch the piezoelectric material, electric current is generated. So what is vice versa of it? When current is passed through piezoelectric material, they will be compressing or they will be expanding. This continuous compression and this continuous expansion give us the sense of vibration. And us getting it. Are you able to visualize when something is constantly compressing or stretching? You can say it is constantly vibrating. Is it? Are you getting it?
Yes, sir.
And this vibration produces sound wave because every vibration produces sound. This vibration is actually above 20,000 hertz. So this is known as ultrasonic sound or ultrasounds, right? Number one. Now, how do we use ultrasonic sound wave for medical imaging? See, we use a probe. That probe is something like this, at the end of which we will be having this transducer or emitter of ultrasonic waves. We will put this probe on patient body and it will generate ultrasonic waves. Now, few minutes back in the beginning of today's lecture, I mentioned one thing. This is the boundary. This is the boundary. Let's say this is medium 1 and this is medium 2. For example, if I put probe on my palm, so air is one medium, skin is other medium. Then ultrasound gets into my body. Skin is one medium, tissue is other medium. When ultrasonic enters the bone, tissue is one medium, bone is other medium. When ultrasound emerges or went beyond bone, bone and tissue is another medium. Anas, are you able to distinguish? When I say medium 1 and medium 2, what does it mean? We are talking about two different surfaces. So we have medium 1 and we have medium 2. Let's say we have an incident beam. It is like this. Intensity of instant beam is I. Now what will happen? This beam is divided into two parts. One will reflect. This is called I R. This is reflected beam. And one will refract. And to avoid confusion between reflection and refraction, we use the term transmitted. This is IT. So if I apply law of conservation of energy, can I say in incident beam is equal to reflected plus transmitted? Are you getting it?
Yes, sir.
I thought you were unable to hear me. So I is equals to IR plus IT. Now it is not necessary that given intensity is divided into two equal parts. Sometimes one part could be zero and one is equal to the given intensity. And sometimes both will be in certain ratio or proportion. It depends upon nature of surface and a property of medium, which is known as acoustic impedance. By the way, quite possible impedance I'm using for the very first time uh, in A2 level because I haven't discussed op-amp yet. When I will be discussing op-amp, it will be very common term. Impedance actually refer to resistance. Impedance is actually resistance. For example, generally in electricity, we say resistance to the direct current is called resistance. Resistance to the alternating current is known as impedance. What is acoustic impedance? Acoustic deals with sound. So acoustic impedance means resistance to the flow of sound with an object. More resistance means less transmission. Less transmission means more impedance. Anas, able to understand it?
Yes, sir.
Now, if you want to calculate this acoustic impedance, it is denoted by Z and it is equal to rho times C, where rho is density of medium, C is speed of sound. So acoustic impedance is given by rho into C. The more the difference between, you can say, acoustic impedance of the two medium, the more will be the reflected ray, right? So when we talk about acoustic impedance, it will surely play a role in that reflection and transmission thing. That will play a role in that reflection and transmission thing. What information we can obtain using the intensities? So one thing, ultrasonic wave will travel, hit the obstacle and bounce back. It is something like echo when sound wave will go, hit the obstacle and bounce back. This will actually gives you information about the depth of the surface. Are you able to understand this point? Remember, we used to say sound wave will go, hit the obstacle, come back, then we can calculate the distance it has actually traveled.
Yes,
So
sir.
when we talk about the time delay, how much time ultrasonic have taken to travel from one boundary to other boundary, this time delay actually give us the information about the thickness or depth of the object. Intensity of the reflected wave give us information about the nature of the surface. There are two information that it will be giving us. One is thickness of the organ, or second is nature of the organ. When I say nature of the organ, what does it mean? Is it a hard surface? Is it a soft surface? So when we examine ultrasonic waves, we can conclude two results. One is how much distance it has actually traveled. So that will give us information about depth or thickness of the obstacle, and the intensity of reflected pulse actually give us information about the nature of surface, right? So what I was saying, when we are talking about two different medium, they will be having two different acoustic impedance, let's say Z1 and Z2. And what did I say? The greater the difference in acoustic impedances, the greater the reflected fraction of ultrasound wave. Now, this is crucial now. When we talk about acoustic impedance of air, what do you think? Does air offer any resistance to anything?
No, sir.
No. And skin must be having much more acoustic impedance in comparison to air. So let's say this is a skin of patient. So when you put this probe on the skin, there is little air in between. Let's say this is air. So this is air skin region. Acoustic impedance of air is almost zero. So acoustic impedance of skin in comparison to air is infinitely large. So greater the difference between acoustic impedance, the more will be the refraction. Can I say in this scenario, all of the ultrasound will be reflected and nothing will be transmitted to human body? Are you able to visualize this thing?
Yes, sir.
So this is what we don't want. We want ultrasound to enter the body. So what we do, normally before taking ultrasound, a gel is applied on patient body. A gel is applied on a patient body. That gel is known as coupling medium. Remember this term, because in exam they do ask about this thing. A gel is applied on patient body, which is known as coupling medium. And what is the purpose of this coupling medium? This coupling medium has acoustic impedance in a manner that almost all of the ultrasonic wave will be transmitted into the patient body. So you can say this coupling medium actually decreases the difference of acoustic impedance, so that we have major portion of transmitted medium than reflected medium or reflected intensity. Anas, getting it?
Yes, sir.
Now, if we talk about intensity reflection coefficient, this is called intensity reflection coefficient. So this intensity reflection coefficient is given by Z2 minus Z1 whole square divided by Z1 plus Z2 whole square. This is the formula for alpha. In other words, you can say this is actually reflected over incident, IR over I. So in numerical in question, we will be using both equations. Alpha is given by Z2 minus Z1, where Z2 is the acoustic impedance of the second medium. So Z2 minus Z1 is square over Z1 plus Z2 square. And if you don't want to get confused, what you can do in the denominator, because it is plus, you call it 1 plus 2 or 2 plus 1, it doesn't make any difference. So keep the order same. Always do final minus initial. So Z2 minus Z1 is square over Z2 plus Z1 is square, and it is actually IR over I. When ultrasonic are traveling inside human body, they will surely experience some attenuation. Or in all medical imaging, we discuss X-rays, they attenuate. We are discussing ultrasound, they will attenuate, and we will be using the same formula. I is equal to I naught e raised to minus k times x. I simply change the variable because mu, we usually use absorption coefficient in case of X-rays. I call it K. If you want, you can call it mu. In some book, they use the same thing. I equal I naught e raised to minus kx, where K is absorption coefficient, where this is absorption coefficient. Now, normally, when we take ultrasound, we perform two different scans. One is known as A scan. What we do in A scan actually measure the distance between the boundaries. So can I say it will give you information about the thickness?
Yes, sir.
So one is A scan. A scan will actually gives you the thickness, and it is relative actually. When I say relative, what does it mean? Let's say we have tissue, we have bone, and we have tissue. And we will put transducer or probe here. So scan A actually try to figure out how far are the different boundaries. Scan will try to identify this distance. It will try to identify this distance so that it can decide what is this distance. I was getting it. That's why I say it is relative. Relative means in reference to the position of the probe. How far apart the boundaries from the probe or transducers. This is A scan. What is B scan? In B scan, we will keep on repeating A scan, but from multiple angles to generate a two-dimensional image. To generate a two-dimensional image. So A scan give us the information of obstacle from the probe or transducer, and B scan help us in obtaining 2D image of the object whose ultrasound we actually want to make. So theory of ultrasound is actually not very confusing. In next class, we will be solving questions related to it. So hopefully in next class, because for on MRI, we don't have many questions. So hopefully in next class, we will be done with medical imaging